Hello, everyone, and welcome to this episode. Today, we're going to be doing a short video on how to find the pH of strong acid and strong base solutions. And it's going to go pretty quickly, but it's something we have to start with before we get into the weak acids and weak bases, which set up their own equilibria. And so let's get started. Grab your calculator and let's get into it. I'm starting with a slide that shows six strong acids that I showed in my last video, and I wanted you to highlight those again and just learn those acids so you recognize them when they show up in a problem that you can say, oh, that's a strong acid and not one of the weak acids. I should mention here that if you Google the strong acids or things like that, you might find some sources, you probably will find some sources that say seven strong acids. And some sources will include chloric acid, HClO3, in this list. And it's kind of a raging debate in the chemistry world with lots of throwing of things and yelling and stomping around. Some people hold that chloric acid is one of the strong acids. Some other sources do not. I remember looking up a while ago for the College Board, and since I teach AP Chem, and they only listed six, so I'm just going to go with six. Try not to be offended by that, and leave me nasty comments or anything like that. So we're going to go with those six. And what's cool about those is that they are 100% dissociated, which makes our life a lot easier as long as we remember which ones they are. All right, now I'm going to start with a question that is going to get us thinking along the lines of the way we need to think when we get into weak acid equilibria and buffers, especially. Because sometimes solutions get really complicated. There's a lot of things floating around in there. And it's helpful to sort of make sense about, okay, which ones are actually the major players here? Which ones are minor players and which ones are, and not going to affect the pH or anything like that. So you'll see this question probably a bunch of times. What are the major species present in a 0.02 molar solution of HI? Hydroiodic acid is one of the strong acids. So when you're answering a question like this, and it's helpful to just do this anytime you get into a complicated, especially buffer problem, just make a list of what's there and what is probably going to affect the solution the most. Obviously, you should always include water. Water is one of the major players in any aqueous solution because that's the thing that there's the most of. It's everywhere. So include water. I'm going to include the fact that there's iodide ion in there because this is a single arrow. And I'm going to include hydronium. But for a strong acid or a strong base, you should never include this guy, the HI, because there really is none of that. I mean, it's there in the equation, but as soon as it hits the solution, it's dissociated, and there really is essentially zero of that in there. So that's not a major player at all. The only major species are the water and then the two ions that it produces. All right, and what is the pH of this solution? Well, once I have the moles per liter of this, 0.020 moles per liter of this, 100% of that gets converted over into the product. So the final concentrations of both of these are both 0.02 moles per liter as well. So I can just take that and transfer that over. So 0.020 moles per liter. And so the pH is simply going to be the negative log of that number, 0.020, which ends up being pH is equal to 1.699 is what came out on my calculator. But a reminder that pH values should always have two decimal places, so I'm going to round that up to 1.70. Okay, that was pretty easy. Let's take a moment and do a pause the video moment with another one of the strong acids, perchloric acid. Take a moment, pause the video, see if you can name the major species and the pH of this solution. Okay, and if you were able to calculate a pH of 2.52, then congratulations. Our major species, again, ignore the perchloric acid part of it because there's really essentially none of those in the solution at all. There may once in a while be a hydrogen ion hooking up with the perchlorate, but it's going to immediately dissociate again anyway. So don't include it. So water, perchlorate, and hydronium. And the pH is the negative log of the molarity right there, which came out to be 2.52. All right, let's talk about strong base solutions. All right, so strong bases. The strong bases are the hydroxides of the alkali metals, lithium, sodium, potassium, rubidium, cesium. I'm not going to include francium because there's really not a lot of that around. And also, barium hydroxide is often considered one of the strong acids as well. So if you see one of the alkali metal hydroxides, that you know you're looking at a strong acid. And to do the same thing, to find the pH of these is just one extra step. And to find the molarity of that strong base solution, since strong bases dissociate 100% in the solution, the molarity is also the concentration of OH. Barium hydroxide is the exception since it has two hydroxides, but use the OH concentration to find the pOH of the solution. The pOH is the negative log of the OH concentration, and then if you subtract that from 14, you will get the pH. So let's try it. We'll start with probably the most common one you'll see is sodium hydroxide. What are the major species present in 0.05 molar sodium hydroxide? Now, this is 100% soluble. That's why it's a strong base. So the major species are water. I'll include that because it's in there. Sodium and hydroxide, but not that. Don't include that as your major species because there's really none of those together anymore. They've all completely dissociated. And what is the pH of this solution? So because this started out as 0.05, then this is also 0.05 moles per liter, and this is also 0.05 moles per liter once it's fully dissociated, one-to-one ratios. So I'm going to go ahead and find the pOH of this solution, which is the negative log of the OH concentration. And the pOH is then the negative log of 0.050. And I got a pOH of 1.30. And then pH plus pOH, we saw in our last video, equals 14. So if I subtract 1.3, so the pH plus 1.30 equals 14, and I get a pH then of 12.70. Again, 2 decimal places on that. And that's how you would do the pH of a strong base solution. And we have one more pause the video moment, so check it out with some lithium hydroxide. Again, pause the video and see if you can name the major species and what's the pH of this solution. And we'll end this video with the solution to this one. If you got a pH of 11.6, then congratulations. The major species are, of course, water. Make sure to list that. Lithium and the hydroxide, but none of the lithium hydroxides themselves. They've dissolved. The pOH was the negative log of 0.004. pOH is 2.4. Subtracting that from 14 gave me 11.60 in my answer. So there you have it. Calculating the pH of strong acid and strong base solutions, and have your log button handy on your calculator. I hope you found this helpful. And in the meantime, have